My name is Quincy Bickerly, but everyone calls me Q-Bick. I'm a math professor at Block University. I have been doing some research on math, and I am here to present my report.
Math and plants? You mean like 2 trees plus 2 trees equals a forest?
Gregory, please tell me you won't do this the whole presentation.
I'm so funny.
Okay, first off, what is mathematics? Mathematics is the science of numbers, quantity, and space. There are two kinds of math: pure mathematics and applied mathematics. Most of what you would learn in school would be pure mathematics, studying how numbers work, graphing, etc. Applied mathematics goes beyond that. Applied mathematics can be found in physics, music, or any subject that uses math at all. Mathematics is a very important subject to learn, whether it be pure or applied. Because math appears so much in our everyday lives, it is important to understand the concept. Take, for instance, plants. Plants use math in just about every aspect. If you look closely at those flowers, you can see... Gregory, stop watching that squirrel and listen! This is a golden rectangle. Golden rectangles are special because their sides have the golden ratio. If you make a square with one part of the rectangle like so, it leaves another similar rectangle. As such, you can create another square and another until the squares are too small to draw. Golden ratios turn up a lot in nature. Also, you can create a golden spiral using these squares. If you draw a curve through each square, it creates an infinite spiral. When a sunflower grows, it stores seeds in the center. They grow out in spirals, but not just any spirals, golden spirals. These golden spirals all fit nicely together as the plant grows.
If it grows in a spiral, wouldn't the plant just curl up on itself after a while?
I guess if it grew for several years. Another golden ratio is the golden angle. The golden angle is about 137.5 degrees. The golden angle is the angle formed when two radii of a circle with area C split the circle into areas A and B. The area of A divided by the area of B is the same as the area of B divided by the area of C. These golden angles appear in the stems and leaves of plants. Leaves tend to grow at different heights, but when they do grow at the same height, they form a golden angle. Moving away from golden ratios, Fibonacci numbers are especially common in plants. Fibonacci numbers follow one simple rule. Each term is the sum of the last two terms. The first two terms are both 1. The next term is 2, then 3, and so on. These Fibonacci numbers turn up in flower petals too. Lilies and irises have 3 petals, buttercups have 5, delphiniums have 8, and Michaela's daisies have 89 or 144.
Where did you get those numbers?
89 and 144 are Fibonacci numbers.
Really?
Yeah. 1 plus 1 is 2, plus 1 is 3, plus 2 is 5.
No, I believe you. So what? Some plants can do math. What's the point?
Plants don't have brains.
Well, that's beside the point. Why does it even matter?
Well, what is the point? The answer is efficiency. The sunflower needs to fit as many seeds into its center as possible. The golden spirals fit very snugly together, so they conserve the most space. Also, golden spirals can go on forever. That way, no matter how much the plant grows, the golden spiral grows with it and retains the shape. Now, this part is somewhat confusing. The leaves need to get as much sunlight as they can. The golden angle is the perfect one for gathering the most sunlight. If the leaves were too far apart, then one might not get enough sunlight and the other would get too much. If they were too close, then they would be forced to share whatever sunlight came in at that angle. At the golden angle, they can get all the sunlight from one half, but none of the sun in the other half. This ensures that the leaves are getting the most sunlight they possibly can.
What is he saying?
The use of Fibonacci numbers in petals also helps to conserve space. The petals are often folded up to save some space for other flowers. To save the most space, a near-perfect circle of petals is formed. These folded up petals form a spiral, and the spiral is closest to a full circle if a Fibonacci number of petals is used.
Well, how do plants do math? Like you said, plants don't even have brains.
Well, yes, I did say that.
Ha! Your presentation is a fraud. Now it doesn't even matter if I was taking notes. Ha!
You weren't taking notes?
Maybe.
Well, nobody is quite sure why these patterns appear. While this could give plants a biological advantage, how would they know how to do math? Have plants been able to do math since the first ones existed? Or have plants evolved and adapted over time to comprehend math? Or can they even comprehend math at all? Well, that's it for my lecture on math in plants.
Yay!
Now it's time for our next lecture.
No!